Welcome to lecture 5. So far we have talked about various types of anisotropic materials. We have seen monoclinic materials, orthotropic materials and transversely isotropic materials. Monoclinic materials have one plane of symmetry, orthotropic materials have three planes of symmetry, and transversely isotropic materials are orthotropic, but at the same time they have one plane with respect to which it is isotropic. And then finally isotropic material is there which has infinite symmetries. Now the composite plies that we deal with are generally orthotropic. So for that because of that we will have special treatment of orthotropic materials in this class. Now we have seen that orthotropic materials have 9 independent elastic constants. So whether we write the stiffness matrix C or the compliance matrix, we have to have 9 independent terms. Now we generally do not directly derive those 9 independent terms, rather with the help of experiments we derive some elastic constants which are also 9 in numbers, and then from those elastic constants we find out the components of the C matrix and the compliance matrix S. Now these elastic constants are quite familiar to us by names, but when it comes to orthotropic they are more in numbers. So the first set of elastic constants are elastic modulus. So in an isotropic material we have just E as elastic modulus, does not matter what direction it is, but here we have E1, E2 and E3, 3 independent elastic modulus in 3 directions. So E is different in direction 1, so it is E1 and accordingly E2 and E3. And then we have Poisson's ratios. Again when it comes to isotropic material we have just nu, does not matter which direction it is, but here depending on the direction we have nu1 2, nu2 nu2 3, nu3 2 and nu1 2 and nu3 2. And then we have shear moduli. So G1 2, G1 3 and G2 3 for shears in different planes. So with this we have total 12 numbers here, 12 quantities here, but nu1 2 and nu2 1 they are related, and so are nu2 3 and nu3 2 and nu1 3 and nu3 2. So these are related, these two are related, these two are related. So with that we can reduce three terms. So we have total 9 terms or 9 independent engineering constants to deal with, and with those 9 independent engineering constants we can define our C matrix and S matrix. Now let us understand the significance of these elastic constants. So let us say we have a material, and if we load it along direction, and let us call this as direction 1. So it will, the effect is it will elongate along direction 1 and contract along direction 2. So if I write the relation here, the strain that is caused in direction 1 is epsilon 1 is nothing but sigma 1 divided by E1, that means normal stress along direction 1 divided by elastic modulus along direction 1. Now apart from causing extension in direction 1, it is going to cause contraction in direction 2, and that contraction is related to the extension in direction 1. So epsilon 2 is nothing but minus nu1 2 into epsilon 1, or we can say that nu1 2 is epsilon 2 by epsilon 1 with a negative sign, because nu1 2 itself is a compression which is negative in the sign. So, to keep this number epsilon 2 is negative itself negative. So, to keep nu 1 2 negative we put a negative sign here. So, this is nu 1 2. Likewise, we can define all the terms. So, we can generalize this as epsilon I is equal to sigma I divided by E I, where I goes from 1 to 3 and nu I j is equal to minus of epsilon j divided by epsilon I, where I j all of them go from 1 to 3 and I is not equal to j. Similarly, we can define the shear strain, which is gamma I j as tau I j by g I j, where I j go from 1 to 3 and I is not equal to j. Now, this is written in double index, that means when they are components of a tensor we write it in this way, but with white notations we can write it like this. So, sigma 4, which is nothing but tau 2 3, can be written as g 2 3 multiplied by gamma 2 3 or g 2 3 multiplied by epsilon 4 as per our notation. So, g 2 3 is sigma 4 divided by epsilon 4 and so on. Now, we will write the constitutive relation in terms of these engineering constants. So, let us say that we have a 3D body in a coordinate system 1 2 3 . So, the coordinate system is 1 2 3 and we want to write epsilon 1, epsilon 2, epsilon 3, epsilon 4, epsilon 5, epsilon 6 in terms of the stresses sigma 1, sigma 2, sigma 3, sigma 4, sigma 5 and sigma 6. So, when it is under sigma 1, so we can call it sigma 1. Now, sigma 1 is going to induce a strain in direction 1, so that is epsilon 1. So, this will become sigma 1 by epsilon 1. Now, similarly, this sigma 1 is going to induce an strain in direction 2, that means it will result in epsilon 2 also, and that we can write as nu 1 2 divided by E 1. Similarly, because of this sigma 1 there is going to be a strain in direction 3, which we can write as minus nu 1 3 divided by E 1. Now, in orthotropic materials there is no extension shear couplings. So, epsilon 4 5 6 are not going to be induced. Now, let us say we load it along direction 2, a normal stress in direction 2. So, because of this normal stress we are going to have normal strain in direction 2 and which we can write as, so this is also sigma 1, this is also sigma 1. So, then here we have sigma 2 divided by E 2 and we can superimpose the effect of sigma 1 and sigma 2 because the behavior is linear. Now, because of this sigma 2 there is going to be strain in direction 1 also, normal strain. So, this is minus sigma 2 by E 1 multiplied by nu 2 1. and similarly because of this we are going to have nu 2 3 sigma 2 divided by E 2. Now, we load it with a normal stress in direction 3 and superimpose the effect. So, because of that we are going to have a normal strain in direction 3. So, it is sigma 3 divided by E 3, and because of the Poisson's effects we are going to have strains induced in other directions. So, those are okay. So, this is sig F E 2. So, and those are minus nu 3 1 E 3, and here we have minus nu 3 2 sigma 3 by E 3. And again there is no coupling between normal and shear. So, even if I give shear, that is not going to cause any normal strain, and similarly these terms are all 0. So, we have no effect, coupling effect between shear and normal. Now, let us assume that in the 2 3 plane we have a shear. So, that shear is sigma 4, and due to that sigma 4 we will have sigma 4 divided by G 2 3, and there is no shear coupling. So, this will not induce in any other shear strain. And now, let us say that in direction in the plane 1 3, that means this shear sigma 5 is also there. So, that will cause sigma 5 by G 1 3, and then we have a shear in 1 2 plane. So, a shear. So, this is sigma 6, and that will cause sigma 6 divided by G 1 2. Now, if I write all these things in a matrix and vector notation, then we have the compliance matrix here, and that compliance matrix is just written in terms of all these engineering constants E 1, E 2, E 3, G 1 2, G 2 3 and G 1 3, and the Poisson's ratio terms. So, with that now we can directly relate these components of compliance matrix S in terms of the elastic engineering constants. So, S in terms of engineering constants. So, with whatever we discussed so far, with that we can write S 1 1 is equal to 1 by E 1, S 2 2 is equal to 1 by E 2, and S 3 3 is equal to 1 by E 3, and S 1 2 is equal to minus nu by E 1 minus nu 2 1 by E 1, and S 2 1 is equal to minus nu 1 2 by E 2, and S 1 3 is equal to minus nu 3 1 by E 1, and S 3 1 is equal to minus nu 1 3 by E 3, and we have S 2 3 is equal to minus nu 3 2 by E 3, and S 3 2 is equal to minus nu 2 3 by E2, and we have S44, the shears 1 by G23 and S55 as 1 by G13 and S66 as 1 by G12. So, these are the components of S matrix, the compliance matrix, in terms of the engineering constants that we discussed so far. Now, we know that C is just inverse of S. So, compliance matrix and stiffness matrix are inverse of each other. So, if I know how to write S in terms of these engineering constants, then just by inversion we can write C in terms of the engineering constants. So, if we do that, this becomes the relations. So, C11 is equal to 1 minus nu 23 nu multiplied by nu 32 divided by E2 E3 delta. C22 is equal to 1 minus C13 nu 13 nu 31 by E1 E3 delta. Similarly, we have C33 where we have these terms nu 12 nu 21 and E1 E2. Now, C12, that is nu 12 plus nu 31 nu 23 divided by E2 E3 delta, and this can also be written as nu 12 plus nu 13 nu 32 by E1 E3 delta. Now, the question is how can I write this? So, that is where the relation between nu 31 and nu 13 comes into picture. So, the relation between nu 13 and nu 31 is just this: nu 13 is equal to nu 13 E3 is equal to nu 31 E1, or we can generalize this to nu Ij Ej is equal to nu Ji Ei. This we will discuss in more details after some time. So, right now we are just using this relation and we can see that with that we can write it like this. Similarly, C23 can be written as this: nu 32 plus nu 12 nu 31 divided by E1 E3 delta, and again these nu 12 and nu 31 they can be changed and we can write them as nu 21 nu 13. Similarly, we have nu 13 here, which can be written as nu 13 plus nu 12 nu 23 divided by E1 E2 delta, and again it can be written in terms of nu 21 and nu 32 with this adjustment. And shear terms are independent. So, C44 is equal to G23, C55 is equal to G13 and C66 is equal to G12. Now, everywhere we have been using this term delta. So, this delta is just defined in this way. So, delta is equal to 1 by E1 E2 E3 multiplied by this determinant of this nus. Similarly, we can write these components of C matrix in terms of components of S matrix. They are just inverse of each other. So, after inverting we can get this relation: C11 is equal to S22 S33 minus C23 square by S. Similarly, we have C22 here and C33 here, and we have C12 and C23 here. C44 is equal to 1 by S4. Again these are pure shear terms, so they are independent. So, similarly, C5 is equal to 1 by S55 and so is C66. Now, while writing this, again we are using this S several times. So, this S is the determinant of this matrix. So, we have defined the engineering constants and we have seen how we can write the compliance and stiffness matrix components in terms of those engineering constants. Now, we will see that there are some constraints on the engineering constants or restrictions on the engineering constants. First of all, we know that C and S are symmetric. C and S are symmetric. So, if they are symmetric, that means Cij is equal to Cji, or we have Sij is equal to Sji. So, if Sij is equal to Sji, we can write nu I j divided by E I is equal to nu j I divided by E j. So, we have talked about the relations between these news, and that is how this relation comes into picture. Now, so that is one constraint, that comes from the symmetry. Second is first law of thermodynamics. That puts a constraint that C and S have to be positive definite. Now, if they have to be positive definite, then the diagonal terms of these individual matrices have to be more than 0 or positive. So, if the diagonal terms of S matrix are positive, that just tells me that, so S positive definite, that tells me that E 1 is greater than 0, E 2 is greater than 0, E 3 is greater than 0. So, they cannot be negative, and similarly we have G 1 2 greater than 0, G 2 3 greater than 0, and G 1 3 greater than 0. Now, C is also positive definite, and we have C, the diagonal terms of C contains is elastic modulus and Poisson's ratio, and we have already seen that these elastic moduli, each of them is greater than 0. So, with that, from the positive definiteness of C matrix, we can write 1 minus nu 2 3 nu 3 2 should be greater than 0, and similarly 1 minus nu 3 1 nu 1 3 should be greater than 0, and likewise 1 minus nu 1 2 nu 2 1 should be greater than 0. And also we define the term delta, which involved some determinant there. So, finally, with that we can write this is greater than 0. Now, we can get some more constraints, because 1 minus nu 1 2 and nu 2 1 is greater than 0. This tells me that nu 1 2 is less than 1 minus nu 2 1, and we know that from the relation between nu 1 2 and nu 2 1 that 1 by nu 2 1 is E 1 by E 2 multiplied by 1 minus nu 1 2. So, with this we can infer that the mod of nu 1 2 should be less than mod of the ratio of E 1 E 2 multiplied by reciprocal of nu 1 2, and again from here we can write just another consequence of this relation is nu 1 2 mod of it should be less than root over E 1 by E 2. Similarly, the other term follows, we have nu 2 1 mod of it less than root over E 2 by E 1, we have nu 3 2 and mod of that should be less than root over E3 by E2, and we have nu 3 1 and its absolute value should be less than E3 root over E3 by E1, and other terms nu 2 3 its absolute value should be less than the square root of the ratio of U2 and U3, and likewise absolute value of E1 3 should be less than the square root of the ratio of E1 and E3. Now, we have completed the discussion on these engineering constants, and we have seen their use, and we have seen how they are related to, how with those we can find out the components of compliance and stiffness matrix, and we have also seen what kind of restrictions they have to follow. Now, let us see just one very simple numerical example. So, here we have the engineering constants of a graphite epoxy lamina, an orthotropic material given, and the material properties are this: E1, E2, E3, nu 1 2, nu 2 3 and nu 1 3, G1 2, G2 3 and G3 1, everything is given to us, and our job is just to find out the components of S matrix and C matrix, and these numerical values are taken from this book by Cow. Now, we already know the relation S11 is 1 by E1. So, if I put these numbers here, 1 by 181 into 10 to the power 9, and that gives us 5.525 into 10 to the power minus 9 meter square by Newton. So, E1, the unit of E1 is the unit of stress or the unit of pressure. So, S is just a reciprocal of it. So, its unit is just the inverse of it. S22 again 1 by E2. If I put these values, and the value that we get is 9.709 into 10 to the power minus 11 meter square by Newton. S33 is 1 by E3, and if we put the values, so we have again 10.3 here. So, E2 and E3 are same, and what we get here is again the same value 9.709 into 10 to the power minus 11 meter square by Newton, and S12 this we have to find using Poisson's ratio also. Again Poisson's ratio is a dimensionless quantity, just ratio of two strains. So, that dimensionless quantity divided by E1. So, that also gives me inverse of Pascal minus 1.547 into 10 to the power minus 12 meter square by Newton, and we have S13, that is nu 13 by E1, and for that we have the Poisson's ratio minus 0.27, and then we can divide by E1. So, we have 10 to the power 9, and that gives us minus 1.492 into 10 to the power minus 12 meter square by Newton, and then we have S23 which is minus nu23 by E2, and if we find out the value, we have 0.6 divided by 10 to the power 3 10.3 multiplied by 10 to the power 9, and that gives the value as minus 5.825 into 10 to the power minus 11 meters square per Newton. And then we have S44, that is 1 by G23, that is 1 by 3 into 10 to the power 9. So, we have 3.33 into 10 to the power minus 10 meter square per Newton, and then we have S55 is equal to 1 by G31, and that is 1 by 7 into 10 to the power 9, and that is 1.429 into 10 to the power minus 10 meter square by Newton. And then finally, we have S66, which is 1 by G12, and that is 1 by 7.17 into 10 to the power minus 9, 10 to the power 9, and that gives me 1.395 into 10 to the power minus 10 meter square by Newton. So, these are the components of compliance matrix S. If we just invert this matrix, we can find out the C matrix, or else we have already derived the relations between the components of C matrix and these engineering constants. We can go via that route also. In that case, whatever expression we got for C11, C22 and so on, in terms of these E's, N's and G's, we have to use that and get the C matrix. Now, if we want to do that, in that case, we may need the other Poisson's ratios also, like nu21, nu32 and nu31. So, if we want to use those, then we have to use those relations. So, we know the relation between nu12 and nu21. So, with that relation we can find out nu21. Similarly, we can find out nu32 and nu31, and once we have those, we can use the formula for the components of C matrices in terms of these engineering constants, and we can find out C matrix. So, either we can invert S, or we can directly use the relations between C and E and E's, N's and G's. So, that completes this problem. With this, I would like to finish this lecture here. Thank you very much.